I mentioned residual plots in our last video, and now we get to talk about them. So here's our previous example from the other video. Right, we said we want to determine which regression best fits the data. We looked at coefficient of determination, and we found that the exponential regression had the highest coefficient of determination. Now what we want to do is look at residual plots. So of course the first question is, what is a residual? Let's look at a particular area of our graph. Blow it up a little bit. Residuals are fairly straightforward. They're simply the difference between our data, yi, and our prediction, y hat. And so to get the residuals, all you really have to do is subtract, and it's always data minus prediction, which means sometimes residuals are positive, which means above the prediction line. Sometimes they're negative, which is below the prediction line. And that's what a residual is. So now what we want to do is calculate the residuals and then plot the residuals. Need to clear some space for this. There we are. And here's our regression equation. And calculating the residuals is very similar to the coefficient of determination, only we're not squaring, which means we have positive and negatives. And what we're going to do is graph L1 and L3. And that creates our residual plot for the exponential. Now what we need to do is change that to our power regression. So that's going to be y2. And we can get our residuals. And then we can plot those. And that's our residual plot for the power regression. And then of course we can change to our linear regression, y3, and get a residual plot for the linear. So if we're trying to determine which is best, exponential, power, or linear, yes, we need all three residual plots. Now, the question is, which regression best fits the data, looking at the residual plots, which of course means we have to ask the question, what do we look for in a residual plot? The short answer is random and rectangular. You can kind of see, maybe starting with the linear plot, that there seems to be kind of a pattern here. I could kind of, I don't know, look at something like that. There seems to be kind of a pattern similar in the residual plot. Doesn't seem to be as much of a pattern here. If I were to draw sort of a rectangle, something like that, these dots seem relatively randomly distributed in this rectangular region. That's what I mean by random and rectangular. So, and what that really tells you is something about the behavior of the data, right? And this is why residual plots are so important. We have our coefficient of determination, which is a really nice number, but it actually doesn't talk about behavior, right? The residual plots really talks about behavior. I'll show you an idealized example of what I mean. So here's an example of a perfectly exponential regression and data. So what do you think the residual plot's going to look like? Well, there's no difference between the data and the prediction, so all of my residuals are 0. Of course, this never happens. The real world is a lot messier than that. But if we look at a linear plot, a linear regression for this, what do the residuals look for that? Well, here I dashed them in. And if we start plotting the residuals, here's the first residual. I'm going to go one by one. All right, we have a negative residual, and the next one is also negative, but a little less. Then we become positive, bigger and bigger. This one is a little bit smaller, and it gets smaller again and smaller. And then it becomes negative, and it's getting bigger negatively. And there we have this pattern that we saw in that first plot. So what we can say is that when there's no pattern, that means there's a good match. It means that the behavior of our regression line matches the behavior of our model or of our data. Where if we see some kind of pattern, that means that the underlying behavior of the data and the regression line seem to be different. That's what generates this kind of pattern. Now, of course, overlaid on this idealized representation is the normal expected variation that we would have in the real world. And that's what's going to create variation. Usually it's a little bit above, a little bit below, different amounts. But if it's this normal variation, you're going to get that rectangular random kind of distribution. And in fact, with a patterned one, you'll also get sort of a range. But again, there'll be this kind of pattern to it, which is exactly what we saw when we looked at our residual plots. So what we can say is because it's random and rectangular, the residual plot for exponential is the best residual plot, which is very convenient that it's also the best coefficient of determination. Now we can ask an additional question, which residual plots can answer, which is very cool. And that is, on average, what size error can be expected? This is actually a very important question, and again, another good reason to do residual plots. The answer is going to be using the standard deviation. A lot of people would say, well, it says on average, wouldn't we just average the residuals? Well, if it's random and rectangular, the average is going to be about 0. Well, that's not very helpful, right? We have standard deviation as our measure of spread. That's really what we want in this case. It's a little bit different than what we did before, because before we were doing one variable standard deviation. Now this is actually a 2-variable standard deviation. It's very similar. We have the big square root sign. We're summing, this is not exactly deviation, it's the error. It's still being squared, divided by not n minus 1 anymore. Now it's n minus 2 because it's actually 2-variable. A little complicated, but trust me on that one. And so what we can do is calculate those squared errors, and then we can go through our sample standard deviation calculation, and we get 2.2, and we should always write that out in an interpretive statement. Most of the time, the measured values will be within plus or minus 2.2 from the predicted value. And you can see, I've put it on the graph over here, it creates this sort of zone of the typical error.